Alright everyone, I wanted to talk about the Tic Tac Toe machine that I made in Tongue, the ultimate nerd game. The first thing you'll notice when you play this is that the screen is animated, and a few people commented about that, and it's actually the most simple part of this computer. And it's so easy to make. And in terms of hooking the computer up to a screen, it's the same way you would hook it up to a screen that is not animated. I'll get to that in just a minute, but let's play a quick game first. He's probably going to win here, although he doesn't necessarily make smart moves. And there we go. So it flashes, and then you can hit new game, and whatever, it's sort of random. It's not, he doesn't pick the perfect move because that's boring. He doesn't pick completely random moves because that has some issues, but it's as random as I could get it with the system I came up with. Probably should have used a pre-existing algorithm for this kind of thing, but I just came up with my own system. It's not perfect, but it's not bad. So, let's move on to how animations work. Now, you'll notice that there are two inputs per pixel. This plotter here, and this plotter here. Tried to get them on one screen, but it didn't really work. This is O, and this is X, and then this is O, and this is X, and O and X. For each of these three panels, it's exactly the same. Each of these tall boards here that have three blotters on top, each of these three blotters represents a frame of animation, and each of these two boards represents either X or O. So if we turn this on, it's going to cycle through these. It's going to go 1, 2, 3, and it's going to stay on 3. Well, forget the stay on 3 thing. It's going to cycle through these. So if you press a button, you can watch the back of the screen here. It's just going to flash through them. It's not going to stay. Now, the input here, which comes on and immediately off again, is hooked up to the last frame. So that means when we press the button, it technically stays on, but since the button immediately goes off, it goes off. So if we use a lever instead, it stays on the last frame. And that's how this works. If in memory we say, oh, there's an O in the bottom right corner, well, it's going to be there for as long as we say it's there, and then as soon as we take it off, it's going to go away. Now you notice that the O doesn't animate itself going away, but the X does. And the reason that is because on an X animation, let's use the back of this board for an example. With an X animation, we have, we can build from one frame to the other while keeping the previous frame. So this means this is frame 1 of an X, this is frame 2, this is frame 3, and so on, until we get our full X. That's how the X works. And then when you turn it off, all it does is it just disables them in reverse order. This wasn't intentional. I didn't animate it backwards. It just sort of happened. So it would go, this is frame 1, this is frame 2, and this is frame 3, this is 0, when it's off. For the O, however, you cannot keep the previous frame, because if you do, like let's say this is frame 1, this is frame 2 of our O, well, you get a filled-in circle. And that's no good. So we have to, each frame, disable the previous frame. So it would be, this would be the last frame. And when you turn that off, it's still going to disable in reverse order, but since the previous two are already disabled, it's just going to turn this one off. That's all it's going to do. That's how animations work. It's that simple. Let's move on to decision making. Here's the decision making boards, and we'll go over how just one board works. How this works is it takes what's already on the screen, it finds the first available spot, and then it takes that as its turn. It's that simple. But it's not really that simple, because obviously that's very predictable. If I were to go in the top left, well, he would go here, maybe. Well, definitely, every single time he would go here. If I were to go here on the first try, you know, this is an open spot, he's going to go here. It's very predictable. Well, what if we said, oh, well, this is the first slot, not this one, but this one. And this is the second slot, and this is the third. Well, if I go here, then he's going to go here. That sort of seems smart, doesn't it? It seems random. It seems random. If I were to go here, well, I think I said this was like the second spot, so he'd go here or whatever. That's how one board works. But instead we have 4 boards, and each computer turn, we pick between one of these 4 boards, and each board thinks the first available spot is in a different place. You can see here each board's orders and each board's outputs and inputs are in a different order. So if I were to go in slot 3, well, he would think slot 2 is the first available spot, which seems smart. Or maybe, if I go in 3, if I go in 3, he's going to think the first available is like 2 or whatever, or if all of these others are taken up. So it seems random, but of course it's not. And so that's how randomness works, that's how animation works. I want to talk a little bit about how win states work. Let's say O took a turn just then. Now it's X's turn. Well, how do we check if O won the game? Well, we take the inverse of whose turn it is. So if it's X's, we invert it to O. So we take O's turn, enable it here so that it goes through all these AND gates. And it is just a series of AND gates. That's how we check to see if anybody won. With a bigger board, like 10 by 10 or 15 by 15, you'd need, well, you wouldn't need, but you'd probably want a CPU to say, how many X's are to the left of me, to the right of me, above me, below me, diagonal, or whatever. And you'd want to check win states like that. But the 3 by 3, it's perfectly reasonable to just have a few AND gates and just run it through those and check to see if anybody won. If they did win, well, there's a clock here that disables and enables the screen input based on who won. So here we have each blotter here is just 1 pixel. Actually, no. Each blotter here is a win state. Sorry, excuse me. So let's say we have the top row. Now this can be either X or O because, depending on whose turn it was last, that's who we're checking. So the other one doesn't matter at all. So if it's all X's or if it's all O's, that's why I put 1s and 0s instead of X's or O's, because it's not just X or O, it's used for both of them. So let's say we get the top row full. Well, we're going to hook this blotter up to, each one of these is pixels, by the way. So we're going to hook this up to the top left pixel, we're going to hook it up to the top middle and the top right. And we're going to use this clock to say, holy crap, doctor scared me to death. We're going to use this clock to say, hey, don't let the screen display anything while this clock is on. But when it's off, display whatever's supposed to be on the screen. So it gives a flashing effect. And it's a really neat way to make a win state. It's very simple, it's very effective, it flashes, it's pretty. So, let's talk now about how the computer makes moves. It's pretty simple. I'm sure it could be a lot more simple. I just went a very robust way of going about it. Here is the tower that decides whether the last turn made is valid, or if the turn that's trying to be made is valid. With the computer, it's always going to be valid, because the computer knows what's on screen, knows how to make a valid move. But for simplicity's sake, we run it through the same system that the player has to go through when he tries to make a move. The player can obviously make invalid moves. Maybe there's an X in the top left, he tries to put an O there. Well, that's invalid. So we have to have this tower to disallow the player from making invalid moves, essentially. So, there are 2 panels here. You can see this front big panel and the back panel. This is just memory. These are registers. Register A is in front, register B is in back. This has nothing to do with X and O, even though there are just 2 of them. This is just for comparison. This tower here, this panel, is an XOR panel. So it takes an input A and an input B. Obviously input A is going to be our register A. Input B is going to be our register B. It checks to see if those are different, and if they're different, it was a valid move. Because if there's an X in the top left, and you try to put an O there, oh, well, maybe you can, but it's still a 1 instead of a 0. Maybe an O instead of an X, but it's a 1. So, it's not going to be different. So it's an invalid move. If it's a blank spot, well, you're changing it from 0 to 1, so it's a valid move. That's how this works. This first panel, when we try to make a move, and these are the inputs, when you try to make a move, it saves to the register and disables the input. And this register leads directly to the screen data, so we can try to write to screen. When a move is made, or in technical terms, when an input is received, when a move is made, oh no, I lost my train of thought. Okay. This first panel of registers, when an input is received, captures the screen. In other words, imagine it's taking a picture of the screen, and it's putting that picture in this folder. Then, we set the screen to whatever this register is, or we add to the screen whatever this register is, because it's a D flip-flop. So, put it onto the screen. Then we take another picture of the screen and write it to this back panel. And then this thing, this XOR tower, oh, I gotta sneeze, looks at the two pictures and says, hey, are these pictures different or are they the same? If they're different, it was a valid move, so let's go ahead and move to the next person's turn. If it's an invalid move, let's just wait for valid. Let's not do anything. That's how this works. That's about all, really. Yeah. So, hope you learned something. Or if not, hope you were entertained, or something. What is this, anyway? Oh yeah, this chooses which board to pick. So these are D flip-flops. And each turn we read from that. Okay. Anyway, see you in a future project.